and I'm definitely mispronouncing his last name, but I'm guessing Falugi.
Yeah, Falugi.
With apologies, who's going to tell us about determinantal point processes in portfolio optimization. So about a 12, 13-minute talk, and I'll wave at you. I'll start waving at you.
Okay. Hi, everyone. First of all, I'm very bad at PowerPoint, so if I make any mistakes, please be patient. So I'm going to talk about determinantal point processes and how we could maybe one day apply them to portfolio optimization. First, I'll give a quick shout out to, yeah, the slides are not very good. Okay, you cannot see everything. I'll try to maybe explain what's missing on the other side. But basically, quick shout out to Odile Maki, who introduced DPPs in 75 in her work, The Coincidence Approach to Stochastic Point Processes. So what's a determinantal point process? So first, so up left there, it's called a point process is just a probability distribution on the power set of a set. So if you have a set chi, it's a probability distribution on its power set. A power set is the set of all subsets of the set. It includes the empty subset in the set itself and everything in between. A DPP is also a random variable on the power set. And so if you want to select a subset J of the set chi, the probability of you selecting it with a DPP is the determinant of the K matrix indexed by J. What's the K matrix? It's called the kernel matrix. You can also call it the correlation matrix or the similarity matrix. It's an n by n square matrix that's symmetric, positive, semi-definite, and has eigenvalues in 0, 1. Now, what's special about this matrix is that it kind of shows the similarity between the elements of J, and we'll go into that in more detail. But basically, a quick example, so we can maybe be clearer, is that let's say we have a set chi that's of length 3, and this is the power set of chi, right? So all this set of subsets. And the kernel matrix K, so K over there, it's going to be this here. This is going to be the correlation matrix. It's symmetric, so Kij is equal to Kji. And let's say we pick J, this subset, out of all the possible subsets. Let's pick, this is our J, right? I want to know what's the probability that J is in the subset we sample from the set with the determinantal point process. And so we take the kernel matrix indexed by J. It's going to be this one, right? So it's shown there, but unfortunately, technical issues. So this is our kernel matrix indexed by the set J. So you take the first row and the third row. So you take the first row and the third row and the columns, and you get these 4 elements, which is this matrix here. And so you calculate the determinant of this, and it's going to give you this. So the probability that our subset J is sampled from the DPP is going to be K11 times K33 minus K13 squared, because again, the matrix is symmetric. So K13 is equal to K31. A big property of DPPs, it's the negative association of the elements it samples. So as you can see so basically it means that when you sample a subset with a determinantal point process, you're going to get a subset of elements that are quite different from each other, that are negatively associated in a way, if you want. So for example, this set of points in this box, clearly they're a bit different. You don't see any overlap between the points, and the contrary to this, where you have a bit of overlaps. It's not very repulsive. So points are you can sample a lot of similar things, while DPP kind of guarantees that you're going to sample items that are a bit different from each other, that kind of repulse each other in a way. And that's like a major property of DPPs. It's why it's useful in many industries. So a bit more about K, the correlation matrix. This K matrix kind of represents the similarity or dissimilarity between the elements. So if you have a set of n elements, you have a K matrix that's n by n, right? And you want to show the kind of similarities between the pairwise elements. So in this case, our K kind of showed the similarities between 1, 3 and 3, 1. This is why 1, 3 and 3, 1 are the same. And so why do DPPs favor items that are dissimilar to each other? Because the more they are similar, the more this term is going to be big, the more the probability of selecting the set that has similar items is going to be small. Right? I don't know if it was kind of clear. It took me a while to understand, but basically, since this represents the similarity between element 1 and 3, and Kij represents the similarity between elements I and j, if you want to sample it from if you want to sample something that contains 1 and 3, the more this is big, the more this is big, the more the probability of selecting j is going to be small. Okay, that's the idea. And also a note that you can sample anything from a DPP, not just integers or points or coordinates. You just have to have a way of quantifying it inside the kernel matrix. You just have to find a way to show the dissimilarities between the items you want to sample, and you should be good to sample it with a DPP. Now, you still have to have a valid kernel matrix, and this is important because this is going to be my main issue for kind of part 2 of my presentation. So this is just quickly a bit of applications of DPP. You have subset selections, like we just mentioned. It's also used in machine learning and video summarization. I was trying to find another application of this because I minor in finance. Okay. And so I was like, can we apply DPPs in finance? So in finance, a very important notion you learn is that when you want to create a portfolio, the more your assets are negatively correlated, the better, because you kind of eliminate or diversify away the risk of a portfolio. Maybe some of you are familiar with this notion. And so what does it mean for two assets to be diverse? Sorry, by the way, I'm so sorry that the left part is not working. But what does it mean for two assets to be diverse? It means they are negatively correlated. So they have a correlation that's negative, not even zero. It has to be like in the negative. And correlations between assets range from -1 to 1. So if you want to create a portfolio, what tool do we now know that can sample negatively associated items? Well, determinantal point processes, right? And so what would be the correlation matrix for this? Can we use a correlation matrix of correlation between the assets ij? Would that work? Well, let's explore. So this is kind of, I wish the left side is important in this slide. But basically, you're gonna, let's say we have n assets, right? So this means you have n assets. Let Ri be the random variable that mimics the return on this asset. So each asset is going to have an expected return. Each asset is going to have a variance, which is our measure of risk. And our portfolio, more generally, is going to be the expected return of a portfolio is going to have the weight of the asset times its expected return. That's basically the expected return of a portfolio. Again, it's variance. And here it says rho ij, so it's the correlation between asset I and asset j. So the correlation of their returns is going to be basically the normal correlation formula, which is covariance over square root of variances. And so the classic optimization problem in portfolio optimization is we want to maximize the expected return you want to get, so mu p, so the expected return of the portfolio, and minimize sigma p, the risk of the portfolio. So it's kind of fair play for every portfolio manager. And so let's say we have a set chi of n assets, a to n. I'm also a bit conscious of time. Let's say you want like a portfolio of negatively associated items, negatively correlated items. Well, we take k, and here it's k. Basically, it's those are the rows, so the correlation between each asset ij. And what would happen if we use this matrix? Well, first of all, we know that a correlation between an asset and itself is 1. So we're going to have ones on the diagonal. Also, we know that correlation ij is equal to correlation ji, and the kernel matrix is symmetric, so we can just mimic these symmetries. So we have now this kernel matrix we know a bit more about. And this is a bit promising, right? Because now we have a matrix of correlations. We know that the correlation matrix K has to represent similarities or dissimilarities between assets. And this looks like it can work. But actually, if a quick n over n equal 2 example can show us that, well, it doesn't really work. And I'll say why later. But basically, let's say we have these assets, so this set of assets, and we have the correlation between the two assets -1. So it's like a perfect world where the assets are perfectly negatively correlated. So surely you want to select them, right? Because it diversifies away the risk of a portfolio. And we show that actually, so if this is the kernel matrix, right? So 1, 1, minus 1, minus 1, the determinant of k indexed by j, and sorry, by the way, I should say that j is this subset. So it's actually the set itself. What's the probability of selecting these two assets? Surely we want it to be big because they are perfectly negatively correlated. But actually, if we make the calculation, we restrict the k matrix by j, which is basically the same matrix because we took the full set. It's going to be 1 squared minus 1 squared is going to be 0. So the probability of selecting perfectly negatively correlated assets is 0. Doesn't make sense, right? We want this to be big because we supposedly prefer negatively correlated assets. And what's the problem here? Well, the problems is, okay, our kernel matrix K is symmetric, but it's not always guaranteed to be positive semi-definite, and it's not always guaranteed to have eigenvalues in 0, 1. And that's mainly the big problem of why we cannot so easily use DPPs in portfolio optimization. Also, another problem you might have noted is that when you sample from a DPP, you might get different samples every time. So which sample is going to be the optimal portfolio? Any of them even? We don't know. So kind of a solution I thought about was there are ways to map matrices to their positive semi-definite forms. There are ways to scale eigenvalues to have them in 0, 1. I didn't have enough time to explore these complicated solutions. But also we can maybe find comfort in assuming that we have so many assets in this world, and we don't care if it's a stock, a bond, or a foreign exchange currency, a commodity, gold, silver, whatever. We just need something that has an expected return and a known risk with it. And usually portfolios only consist of 25 to 30 assets. So maybe if n is not so big, we can maybe construct something in the future or find a solution. But yeah, that was basically my presentation. Thank you for listening. I have to throw a shout out to Hannah, the best DRP mentor that couldn't make it. I think she's a bit late, but yeah, thank you very much.
Okay. Any questions?
Yeah.
Is matrix 1 minus 1 minus 1 1?
Yeah.
So I think it is positive semi-definite and or like I guess it's like if this matrix
This matrix. I actually didn't even compute the eigenvalues of this matrix, but generally, if you have a set of n assets and you create an n by n matrix, it's very unlikely that you're going to have a positive semi-definite symmetric and eigenvalues in 0, 1 matrix. Generally, I didn't really try for this one, but I mean, I could right after this. Yes, unfortunately, it doesn't work. Yeah, we didn't find the $1 million idea, but maybe next time.
Are things better if you make the range of associations 0 to 1 instead of 1 to 1?
So we actually explored this idea. We actually wanted to make it from 0 to 2, not 0 to 1. But I don't know. It didn't really seem like we're just artificially changing everything from -1 to 1 to 0 to 2. It didn't really seem good. Also, I've tried a few examples. Like maybe show you guys. I was sketching some stuff. I hope I can find it. Yeah, so I tried to scale it. So this is a matrix, right? That the correlations are from -1 to 1. I tried to change everything to the range 0 to 2, and it also didn't work, right? Because when I computed what are the probability of getting the one and the second element inside the sample, it also gave us, it gave us like a not valid probability distribution where the probability became 4, which is not a valid probability distribution. I think the restrictions on the kernel matrix are there to ensure that we have a valid probability distribution. Yeah? You can ask me after maybe if I. Okay. Thank you, guys.
Thank you very much. I'm doing a board talk, right? Yeah. I'm so sorry about the.
I'm sorry.